Hello, we are Group 15. In this video, we will introduce our machine learning project, Predict the Battle Finals of PUBG. We will illustrate the project in these 5 aspects. Firstly, let me explain what is PUBG. PUBG is an online battle video game. During the game, 100 players are dropped onto an island, empty-handed, and must explore, scavenge, and eliminate other players until only one group is left standing. All while the play zone continues to shrink. And in this project, we are giving over 65,000 games worth of player data, split into training and testing sets, and asked to predict final placement from final in-game states and initial player ratings. Next, we will introduce our dataset. These are our training dataset and testing dataset. Every row in the dataset stands for one player's post-game states, and the columns are the data fields. The data fields including DBNOS, which is the number of enemy players knocked by this player. Assists, number of enemy players this player damaged that were killed by teammates. Boosts, number of boost items used. Damage dealt, total damage dealt by this player, etc. To make data feature more accurate, we did data cleaning. Firstly, we fill up the absent data. We checked the non-data in the dataset and fill up the non-data with its data field mean value. Then we eliminate the abnormal data. Next, we did data inciting and feature engineering. In order to extract new useful features, we analyzed the data, which will help us improve the prediction accuracy of the model. Firstly, we counted the killings of all players. On average, each person killed 0.9 players. 99% killed 7 or less, and the highest number of kills was 72. Then we draw the walking, riding, and the swimming distance distribution maps respectively. From the graph, we can see that the majority of players have 0 swimming distance and 0 riding distance. This figure is the Pearson correlation coefficient of all features. We know from the figure that from the perspective of target variable win place percentage, only a few variables are related to it. The highest contact variable is walk distance, and the lowest contact variable is kill place. And then we focus on the 3 highest contact variables, which is walk distance, boost, damage dealt, and the lowest contact variable, kill place. And we draw the scatter plots of them and the winning position. This graph shows the relation between walk distance and win place percentage. Higher walk distance always leads to a higher win place percentage. This graph shows the relation between boosts and the win place percentage. Higher boosts always leads to a higher win place percentage. Similarly, this graph shows the relation between damage dealt and win place percentage. Higher damage dealt always leads to a higher win place percentage. Next, let me show you the relation between lowest contact variable, kill place, and the win place percentage. We can see that as the kill place decreases, the win place percentage will increase.
After we finish data insighting, we start to do the feature engineer. In order to get a better result, we engineered more features from the given features. First, we created a player's real feature by group by on match ID, giving total players who played in that match. Up to 100 players can compete in one game, but usually most games are not full, but no more variables tell us the actual players involved in each game, so we create this feature. The 100 players are definitely easier to find and kill than the native players. So according to the feature player's rule, we built a killing score and damage scores named kills norm and damage dealt norm. We set the standard like this. You can get 1 point for killing each enemy in a 100 players match and get 1.1 points for 90 players match. Similarly, we also group by on group ID to get actual group size features of that player, since it is not necessary that a squad game will always have teams of 4. Next, since distance traveled has a high correlation with the win place percentage, we add a new feature total distance, which is a sum over the swim distance, ride distance, and walk distance of the player. Since boosters and hills both can help players to travel faster, we add a new feature which is hills and boosters. This is the sum of hills and boosters. We also created the feature total atom. This feature combined all the atoms used like boosters, heals, and weapons. Since number of items used more might indicate the player stayed longer in the game, and hence might contribute to win place percentage. Finally, since generally better teamwork may lead a better result, we added 5 new features based on group size. First is atoms used per team, which means total atoms the whole team has used. Second is kills per team, which means the total kills of all players in this team has performed. Third is damage dealt per team, which means the total damage dealt by this player's team. Fourth is kill points per team, which means kill points over the whole team. The final one is kills per distance, means the person be killed in 1 unit distance. And this is the head of train dataset after the feature engineer. Part 4 is about our model selection. After the data processing, we have trained several machine learning methods, and last, we decided to use random forest and XGBoost. Random forest is a supervised learning algorithm. As you can see from its name, it creates a forest and makes it somehow random. The forest constructed is the integration of decision trees, and most of the time it is trained by the bagging method. The bagging method, bootstrap aggregating, uses random and playback training data and constructs classifiers. Finally, the learned model is combined to increase the overall effect. XGBoost is an optimized distributed gradient boosting library designed to be highly efficient, flexible, and portable. It implements machine learning algorithms using the gradient boosting framework. XGBoost provides a parallel tree boosting that solves many data science problems in a fast and accurate way. The same code runs on major distributed environment and can solve problems beyond billions of examples. And the last part is the experimental results and conclusion. This is our MAE loss table. It contains a random forest and XGBoost model in each training set and validates the performance of the dataset. For the integration method, the performance of the XGBoost enhanced method is superior to other models because of its strong nonlinear data fitting ability. In addition, the MAE values obtained by XGBoost are more stable in each training and validation datasets. But in random forests, the MAE values of validation and training sets are surprisingly different. Finally, through the comparison and analysis of MAE value and the final predict data value, it is found that the predict results are not very different. But the value of MAE is more stable in XGBoost, so we choose the XGBoost model in the last. We limited ourselves to the cargo problem statement that predicts the winning percentage for all participants in the dataset. We can also use previous data to predict other statistics, such as deaths, walking distance, and health. This prediction can be made on an entire dataset or on a more fine-grained scale, such as by team or by match. At the same time, since cheating players play an important role in statistics, we can try to find the patterns and build models on these players, because they have a relatively limited choice of plug-in software. Another possible approach is to stratify games according to the average player level, since different levels of games may have different optimal strategies. The results show that the XGBoost algorithm can learn nonlinear relation better and faster. We also learned about the importance of exploratory data analysis and feature engineering in machine learning. EDA helps us find traces in data and understand what types of pre-processing are required. We can also use these insights to add new capabilities to enhance the robustness of the model. And this is all about our project. Thank you.